Yeah, hi, good morning everyone. My name is Rohit. I am a software engineer at Meta. Today I will be speaking on the boundary clocks versus transparent clocks in hyperscale network like we have at Meta. Um, so what basically I want to cover is, I know in my the previous presentation covered a lot of pros and cons on boundary and transparent clock deployments. So basically I'm going to just briefly talk about what those pros and cons and how they actually interacted and how we use those to make a decision on how we're going to be doing the deployments using FBOSS in the Meta data centers. And of course, then we ran into the challenges on the scaling side and how did we resolve those. Boundary versus transparent clocks, I guess we've already gone through some of this stuff. It's basically boundary clock is something where we would actually terminate the clock at intermediate nodes. So a grandmaster would actually be terminating its packets or sessions to a boundary clock who acts like a slave, and then it acts like a master for the downstream nodes. And so on, and basically there would be a chain of boundary clocks, and then they connect to the ordinary clock, which acts like a slave to the master side of the boundary clock. It's the most common known node or the clock type, and obvious advantage of this is that it's a point-to-point synchronization and it scales really well. Especially in a data center where you have lots and lots of nodes and hierarchy, this kind of actually is a pretty useful thing to have. Transparent clock, this is a very similar looking diagram, but in a different way. There is a server on your right side, and then there is an ordinary clock on the left, and we are sending traffic across the PTP event messages, and there is the offset that gets calculated on every node. Transparent clock node, and that offset is actually set into the packet and transferred over to the OC, and of course then OC would return back the packets, the delay requests, and response transaction would happen, and because of this transaction we would be able to calculate the clock offset, and the ordinary clock can actually tune the time very close to the OTS. And the advantage obviously is that we are able to take care of the residence time that is being spent on each node. The transparent clock, it's the same thing. Basically, there is a CF, which is the offset that gets into the packet. It is calculated on every node, and every node is going to insert its residence time into that packet, into the PTP packet, into the CF field. And as the packet progresses across the chain, across the whole data center, that offset keeps getting added up so that the ordinary clock can know the exact offset to use to calculate the time. TCs obviously do not need to recover the time. That's a great benefit. It uses less expensive oscillators, and they don't need to be just very accurate, just like a boundary clock does. Its transparent clock is ideal for heterogeneous environments where we have network with different hardware capabilities. In a data center, we could have hardware which has various degrees of functionality in there. Some can support some versions, some can support others, and it looks like this transparent clock is an ideal way for us to actually deploy within a network, even if some of the nodes in the DC do not speak transparent clock or do not understand or support every aspect of PTP. Obviously, it's significantly easier to implement in software as well and deploy in the network as compared to a boundary clock. There is less of a hassle in actually productionizing and pushing such feature into the production zones. So in the Meta DC, when we started looking at Explode, we did go with PTPTC in end-to-end mode. Uh, it uses the underlying hardware timestamping to enable the feature. Uh, Obviously, the TC in the P2P mode is a lot more accurate and scales much better, but we still went with E to E mode because it's the simplest one to actually implement in a system. Intermediate nodes in the network are not really required to support PTPTC. It does reduce the accuracy of the clock, but if you could have enough nodes inside your network which actually support it, we could actually, or we hoped we would be able to get it to a decent accuracy. So one of the DCs that we were able to upgrade, we actually used PTPTC and we were able to actually upgrade the whole network within 3 months. And that's actually pretty amazing given that if we had gone and taken the option of BC boundary clock, it would have taken a lot more effort just to develop the BC. And obviously then we have to support it and troubleshoot it in multiple ways. So TC also is light on debuggability or debugging aspect of it. And in the end, we did find that PTPTC provide enough clock accuracy to meet our application requirements of around 95th percentile accuracy of 400 nanoseconds, which works well for several applications that want to use PTPTC in our DCs. This is just a kind of a diagram of how within 4 months or within 3 months we were able to actually push and deploy the PTPTC into an entire DC network. It was actually was pretty amazing. We didn't have to actually backtrack or kind of pause our push because of any issues and stuff. We did run into small issues early on, but we were able to navigate through them and safely deploy this into the network without causing any incidents or disruptions. And of course, the TC, as in Meta DC, is IPv6 only network. The next aspect is the scaling challenges with PTPTC. We already talked about boundary clock being the most scalable one, and PTP point to point being closer to it, and we don't do either of them. We do PTPTC in end-to-end mode. There is no multicast in the network, so each slave is going to actually create sessions to the master clock, and that puts a lot of actually overhead on the masters because it has to maintain state for a lot of slaves. And we are talking, I think, of the order of 500K slaves or sessions that the server has to maintain. There are other challenges that we run into. We need redundancy in the DC. We just cannot rely on one clock source for the original time. What if that clock source goes down? What if the network where that clock source is being sourced from goes down and stuff, right? We had actually a very ambitious idea of operating unaffected even if we lose 55% of time sources in a data center. So basically, even if we lose 3/4 of our grandmaster clocks in the network, we should still be able to continue running. And of course, I already talked about the reliability. So how do we go about solving this problem? This is an example of how one of the data center fabrics look like. There is a grandmasters that are connecting to an FBOSS enabled, TC enabled switch. And those switches actually hook into the CLOS network, which has all the other fabric switches and rack switches. And obviously there is an ordinary clock at the end. And basically in a given data center, we start with 4 sources of clock. These are all different grandmaster sources. All the nodes in between are ideally required to have PTPTC, but as I did mention, even if we can actually propagate TC to many nodes, we still can get a decent accuracy. And upgrading them to actually run TC has been a fairly easy task as compared. So the scaling challenges, the way we solved this is that we started scaling the PTP server, which is P2P4U. It was actually, we made it work with 75K clients. It was able to actually handle 75K clients at the time when I started writing these slides. And it was able to generate the syncs and session for about it was able to handle 300K requests per second. That's good, but actually now we are able to scale all the way up to 1 million clients per server. And basically all of this is obviously open sourced, and what that basically means is that effectively one grandmaster, as we had in the previous slide, can operate on its own and serve the whole data center even when all the other 3 grandmasters go down for reliability. Effectively, even the biggest of the DCs that we have actually have up to 500K clients, and with we able to scale to 1 million clients, we are able to solve the scaling challenge and bring reliability into our system. This is how, I'm sure this slide might have been used elsewhere, but basically this is where how a PTPTC looks like in our data center. There is a bunch of racks which actually are hooked up to the grandmaster clock, and they are propagating the packets through a network of nodes which are all transparent clock ideally. And at the end is a server or an ordinary clock, which is a PTP4L, which actually terminates this clock and uses this packet exchange to actually correct its clock. That's mostly is call to action. Please join the Time Appliance project if you could contribute to it or with any suggestions you might have. With that, I think I am kind of open to questions. Okay.
Thank you, Rohit. So we're open for questions. Maybe we can elaborate on, again, the quality of the oscillator on the transparent clock. So that was your question. Do you want to add something to it? Like, let's say, like the importance of it and what are the determining factors?
So as I understand, like in the transparent clock, the quality of oscillator is obviously important in all the intermediate nodes, but it's not as important for transparent clock because it's just a residence time. For a boundary clock, I guess the oscillator needs to be a lot more accurate because it needs to be a clock source and it needs to sync up the time and regenerate the time, right?
So one interesting thing also with a transparent clock is, again, when it comes to accuracy versus precision, if you don't have a mechanism like, let's say, a servo to compare the accuracy of your oscillator versus let's say a grandmaster or open time server. Therefore, you rely on the accuracy for the manufacturer. Although residence time is small, but you are relying like on whatever that oscillator is. Like oscillator is at 10 megahertz, let's say, with so much ppm. That's what you're going to work with. So what is interesting here is if you look at remember the chart where the RGSW is sitting, basically RGSW sits right on the top of the can we get the slides back? Yeah. So yeah, no, you have it. You have
okay. Oh, cool.
So RGSW, is there a laser in that thing?
This will work, yeah.
I think so, yeah. So RGSW is basically sitting here, right? And let's say if any of these transparent clocks, as you go down the tree, they have, let's say, a problem with the accuracy, it will show up because then on the end nodes, you will see a drift. But the problem is when you have the RGSW having a drift. So perhaps if there is some improvement, let's say you want to have an improvement on oscillator, you should probably invest a lot on this one because this really sits on top, and then you will not have a good way to determine like where like the discrepancy is. Yeah, please come to the microphone.
Yeah, let me just respond. Yes, you're absolutely right. But regarding for the oscillators contribution for those synchronization, the whole system, I think, if you keep with all those kind of the input, the timing clock input, like GPS, you keep that, no problem. PTP master clock, keep doing the good job, no problem. Even go to the physical layer. Let's see, Sync E still working fine. The most important factor is just assume all the disaster situation happened. You lost it all. In that kind of a case, that's why oscillators hold over accuracy.
In boundary clocks.
In the boundary.
Which therefore, like
transparent.
we are all with transparent clocks.
Yeah,
that's
I agree
why,
with you. It's the transparent.
Yeah, that's why you have like this redundancy. Like you can switch. You have 4 of them, and then there are 2 of these, and this is like 1, and there is another 2. So in total of 16, let's say, for every data center, and 1 is capable, more than capable, to handle the entire data center.
I think this is maybe the hot topic for TAP group to consider. Such as that the data center profile. Do we need to define what's going to be the the backup or fault tolerant? How many in the timing basically is resource we need to reference? 2, good enough. Meta using the 4, good enough. You mentioned about maybe up to the 16. Right? So those things are hot topic.
Thank you very much. Thank you.
Thanks. Thank you.
Kevin?
Yeah, question about the TC itself. So end-to-end makes sense. You can incrementally deploy and incrementally get benefit on the path. The residence time, I didn't see any distributions or that you've measured. Do you have that data in terms of what are the residence times that you're actually seeing in practice?
We had a test Yuri performed on the booth. Yuri, do you want to speak on that? Yeah. Go to the microphone, Yuri.
The resonance time, what's the distribution? Max, min? The resonance time for a transparent clock?
Yes.
Using a crystal or using an OCX. So when we use the
No,
OCX...
just the residence time, like basically before we do the correction, you can see the push.
Actually, I don't know exactly. Amit, can you say
From what I remember, it was like around 1.2 microseconds.
I don't remember.
No? Okay, let's see, Amit.
Too many tests.
Residence time, it has a lot to do with the network, the traffic load in the network, obviously, and how the switches, if they experience congestion, and what kind of quality of service mechanisms you're using. So it's really I think a network by network question. We can tell you that when the network is not loaded, you can expect like pipeline delays, probably about half a microsecond, maybe less.
That's what I was pointing at. Like in our demo here, we're not loading.
The demo
buffers.
here is not loaded. The system is not loaded, so I don't think it's representative of.
Right. Yeah, I think it would just be interesting in terms of the 95% you were talking about,
range.
right? The range in operation. Of course, you have to assume some worst case residence time with some worst case PPM or PPM per second if you're compensating for that.
So perhaps, Rohit, do you remember some numbers before we enabled transparent clock in terms of error? Or you see the error that you see when transparent clock is not enabled? Because that's directly a representative of distribution.
Right. No, actually, we did not do those measurements because, we did measurements for some other purposes, but as been pointed out, that it depends upon really how loaded the network is. So if you have a lot of congestion happening, the residence time can actually go to more than a microsecond as well.
Of course, yeah. Do you know range, like let's say the pipe, just the pipeline, when you don't have anything, it's like half a second. When we are congested, like not congested, like 60-70% normal operation, you get what?
I'm not exactly sure on that, but yeah, it could go to 2 microseconds and stuff.
It'd be interesting just looking at the correction field received
Yeah.
by the OCs. Then you'd have at least the sum. You could take an average. Or
That's why
Right.
we use the Sentinel, the Calnex Neo device, basically to show us like the range and then what's the forward and backward error and the correction.
Good. Thank you.
Rindra, you might want to.
So in the data center, all the switches are shallow buffer switches. So if you take the pipeline latency up half a microsecond, I mean, there's an upper bound on how much the packets can get buffered. And it's not going to be like in milliseconds. It's going to be like a few microseconds.
Which that basically, with the consideration of, let's say, 4.6 ppm on the oscillator, really makes it negligible, takes it really down to the floor noise, perhaps. So, but boundary clock, I totally agree with you.
I think now here is also, regarding for the different kind of the parameters we're looking for.
Yeah.
This along the pipeline, well, what's the total accumulative?
Yeah.
The frequency offset or time offset.
Yeah.
So maybe just think about this for the tab.
Yeah.
We may come out to some testing methodology guideline, maybe helpful, so we can talk
So we
in the
have
same language.
a work stream. Gary is leading it, the oscillator work stream, which a lot of these classifications are already there. So Gary has a table that soon it will be contributed as another OCP contribution, which has for different appliances, transparent clock, boundary clock, ordinary clock, grandmaster, you name it. What are the specs we're like suggesting, and what are the classes? So stay tuned, or reach out to Gary.
Yeah.
A lot of work has been done last 6-7 months.
Excuse me.
Yes.
Yeah, thank you for sharing this information. And my question is more regarding to the scalability challenge for transparent clocking.
Sure.
And you have reached this milestone, can handle 1 million client. Will it be good enough for your data center?
Yes. So yeah, I think as I mentioned, most of the data centers that we have actually go up to 500K clients. Even in our largest of data centers, we're going to be.
I'll get you the screen. Can we get the screen?
This one, do you have the? Oh, it goes now. It's a little bit slow in response. Thanks. Yeah, so it does actually, even the biggest data center that we have would have up to 500K clients. And in bigger data centers, we'll likely have more than 4 of these grandmaster clocks there. So yeah, I think with 1 million, yeah, we kind of cover almost all scenarios in foreseeable future.
Where boundary clocking will be on the table for you consider, in terms of scalability as you moving forward.
Right. So I mean, boundary clock obviously we know is going to be. So I guess your question is that would boundary clock be better in terms of scalability? Is that?
Yes. Will you consider the boundary clocking as you moving forward? As one of the options.
Yes, definitely we are considering it. But the advantages kind of in terms of quicker deployment and quicker productionizing was so heavily skewed towards transparent clock that we had to go into that direction. But I'm sure going forward, the requirements of our applications may want tighter bounds on the timing. Because right now the accuracy is in few hundreds of nanoseconds, and they might want even a tighter bound, at which point I think it might make sense for us to explore boundary clock.
Thank you.
Thank you.
I just wanted to say thanks to the community. For those of us who've been involved in it for a long time, amazing progress in just a couple of years. And to see the scale is really amazing, as well as the openness of the community. Okay, 1 year, thank you. The openness of the community just to drive this forward, make things open and available, and working together. Really great effort. Thanks, everybody.
Thank you.